Hey everyone, and welcome to today's Explainer. Today, we're diving straight into defeating the EV range killer and exploring the silicon carbide revolution. We're going to take a deep dive into the hidden physics of electric vehicles and uncover a massive material science breakthrough that is fundamentally flipping the auto industry on its head. It's a pretty incredible story about atomic structures, intelligent energy management, and reclaiming power that used to literally just vanish into thin air. So let's get started. So let me pose a bit of a mystery to you. Your electric vehicle is leaking energy every single second you drive it. But where is it actually going? Now, most EV owners instinctively point to the obvious culprits, right? They assume the battery's draining rapidly because of aerodynamic drag pushing against the car, or maybe it's friction from the tires gripping the road. Or logically, you might even think it's the electric motor itself just being a bit inefficient. But the truth is, modern electric motors are already incredibly efficient, often topping 95%. The real culprit that's actively stealing your driving range isn't any of those things. In fact, it's completely invisible from the outside. That invisible true range killer? Well, it's hidden deep inside the power electronics of the vehicle, in a component called the power inverter. See, every single time you accelerate your EV, there are thousands of electronic switches inside this inverter that are rapidly turning on and off, controlling the flow of power from the battery to the motor. And for years, these conventional switches have been wasting highly valuable battery energy by converting it directly into heat. Heat that serves absolutely zero purpose. Heat that literally glows if you look at it on a thermal camera and is just steadily robbing you of your driving range. Okay, let's dive into this and look at what the inverter actually does. Think of the inverter as this absolutely critical translator between the battery and the motor. Your vehicle's battery stores direct current, or DC electricity, but your motor, well, it needs alternating current, or AC electricity, to actually turn the wheels. So the inverter has the monumental task of performing this DC to AC conversion thousands of times every single second. To pull off that massive workload, it relies entirely on those rapid power semiconductor switches we were just talking about. And as it turns out, the type of switch you use changes literally everything. And this brings us to a major technical showdown that is completely redefining automotive engineering today. Historically, the switches inside EV inverters were made of traditional silicon, specifically these things called insulated gate bipolar transistors, or IGBTs. Now, while these Silicon IGBTs have been a reliable industry workhorse for decades, they have a major fatal weakness when it comes to modern EVs. They are just relatively slow. So today, they are being rapidly replaced by next-generation switches made of a totally different material called silicon carbide, which forms SiC MOSFETs. But to understand why this shift is so absolutely crucial, we really need to understand exactly why traditional silicon is failing us in the first place. The core problem with those older silicon IGBTs comes down to a phenomenon called tail current. Every time an IGBT tries to turn off, it doesn't just stop instantly. Instead, it spends this brief moment in a partially conducting state where the current continues to flow or kind of tail off. Think of it like trying to stop a massive freight train. Even after the brakes are firmly applied, the train just keeps rolling forward for a bit because of all that momentum. Well, in an electronic switch, that lingering, sluggish tail current is highly problematic. During that slow, sluggish transition caused by the tail current, there's a brief microsecond where both high voltage and high current exist in the switch at the exact same time. Basically, they overlap. And in the world of power electronics, when voltage and current overlap, energy is immediately lost as useless heat. Now, a microsecond might not sound like a huge deal to you or me, but when you multiply that tiny energy spike by tens of thousands of switching cycles every single second, and then multiply that by every minute of every drive you ever take, it creates a constant, massive stream of thermal waste. Energy that should be pushing your car forward is instead just baking the electronics. To really understand why this happens, we have to zoom all the way down to the sub-microscopic, atomic level. The root cause lies in a fundamental property of silicon called its band gap. Now, the band gap is simply the amount of energy electrons need to absorb before they can jump around and move freely within a semiconductor material. Traditional silicon has a relatively narrow band gap, and because it's narrow, electrons can jump across a bit too easily when they're under extreme stress. This narrow band gap results in higher leakage currents, greater heat generation, and fundamentally lower efficiency when exposed to the extreme voltages and temperatures demanded by modern electric vehicles. Silicon has, quite simply, reached its physical limit. And this is exactly where silicon carbide enters the story and absolutely changes the game. Silicon carbide, or SiC, belongs to a very special class of materials known as wide bandgap semiconductors. In fact, the bandgap of silicon carbide is nearly 3 times larger than that of conventional silicon. That single, invisible atomic property is the absolute key to defeating the EV range killer. Because of its tremendously wide bandgap, a silicon carbide MOSFET can withstand much higher electric fields before breaking down. But far more importantly for our inverter, it completely eliminates that sluggish tail current problem we talked about earlier. While a traditional silicon IGBT struggles and drags its feet through each switching event, a silicon carbide MOSFET just snaps on and off almost instantly. It's clean, it's precise, and it is incredibly fast. And naturally, the faster the transition, the less time voltage and current have to overlap. Now, what's really interesting about this slide is the sheer scale of the resulting efficiency gain. Because silicon carbide snaps off so instantly without that trailing current, switching losses drop dramatically. And we aren't just talking about a 1 or 2% improvement here. Depending on operating conditions, silicon carbide technology drops switching losses by a staggering 70 to 80% compared to traditional silicon. That is a massive amount of battery energy that is no longer being converted into useless heat. Instead, it's being sent directly to the motor to propel the car. And the benefits of this molecular efficiency gain don't just stop at the microchip. They trigger this amazing cascading domino effect throughout the entire vehicle. Step 1, the inverter generates significantly less heat. Step 2, because there's less heat to manage, engineers can drastically shrink the size of the liquid cooling systems, which means smaller radiators and smaller coolant pumps. Step 3, less thermal hardware means lower overall vehicle weight. And finally, step 4, every single kilogram you remove from an EV contributes to even greater macroscopic vehicle efficiency. It's honestly amazing to think that a tiny atomic tweak ends up shedding physical weight from the entire car. Engineers in the automotive space often summarize this with a very simple yet powerful engineering principle. Cooler is faster. When your power stage is running cool, it avoids a problem known as thermal throttling, which is basically when a system has to artificially slow itself down just to prevent melting. A cooler silicon carbide inverter can sustain its peak performance for much longer, which gives the driver better acceleration consistency, vastly improved reliability, and uninterrupted efficiency. So the crucial point is, what does all this molecular science actually mean for you behind the wheel? Well, it delivers a very real-world consumer dividend, a 5 to 10% boost in usable driving range. By simply changing the semiconductor material inside the inverter, the entire vehicle literally travels further on the exact same charge. Let's put that into perspective for a second. Imagine an EV that consumes 18 kilowatt hours of energy for 100 kilometers. If it has a baseline range of 500 kilometers, upgrading to a silicon carbide inverter can yield 25 to 50 additional kilometers of driving distance. And I want to be incredibly clear here, this extra range is not coming from cramming a larger, heavier battery pack into the floorboards. It's not coming from a lighter body frame or stripping out the interior either. It is coming purely from intelligent efficiency. It's reclaimed energy that used to just bleed out as useless heat. But extending range is really only half the story. Silicon carbide is actually the necessary foundation for the entire future of the EV industry. The next generation of electric vehicles is rapidly moving away from standard 400-volt systems and shifting toward 800-volt and even 1200-volt electrical architectures. Why? Because these high voltages allow for ultra-fast charging, massively higher power outputs, and thinner, lighter copper wiring. But traditional silicon, it simply cannot survive these extreme high-voltage environments without overwhelming thermal losses. Silicon carbide is the enabler here. It's what makes these advanced, high-power architectures practically possible. So it turns out the hidden range killer was never the battery. It was the heat. By replacing traditional silicon with silicon carbide, we are finally defeating that thermal waste and using every single electron more intelligently. So I'll leave you with this provocative thought. If we can reclaim up to 10% of a vehicle's range just by changing the atomic structure of a few switches, what other limits will the next generation of electric vehicles shatter as they continue to master intelligent energy management? The road ahead is incredibly bright, and it's running cooler than ever. Thanks so much for joining me on this explainer, and keep your curiosity charged.